Now we will talk about inorganic metal halides. We will be talking about a couple of representative examples how in a real material science one can use solid state NMR. Again, I have to admit probably tomorrow Dr. Shashi Kumar would address about solid state NMR, where he talks about how whenever I am taking a liquid, okay, molecules are rotating or freely moving in the system. Hence, your relaxation time is different. Whenever I take solid, then they are bound system. They cannot release their energy immediately. Then it is hard to get good NMR spectrum. For that, what they do, they make your sample to tilt at particular magic angle, okay, and then they spin the atom, they spin the material, so that during that motion artificially we make it to move like liquid, and then I get high resolution spectrum very much similar to that. Okay, I never do that. I don't artificially make it to vanish the dipolar interaction among two spin systems. Okay, I measure it as it is. Okay, that's why whenever you do little background verification, this fellow talk differently and what I say differently, that is a major difference. I did not even mention about that magic angle NMR. That's why many people work on solid state mass NMR, MAS, magic angle spinning NMR. There is a term called 3 cosine square theta minus 1, dipolar interaction. Read again 1 minus 3 cosine square theta. Term will be there in one of the interaction Hamiltonian term. They try to make this one 0 to go to 0, and then if a substitute can calculate for what value of theta that shall become 0, that becomes about 34 degree. I don't remember now the exact number. Okay, at that point, instead of keeping your sample this way, they tilt it at 34 degree. Then make it to rotate it. How do they rotate it? They send one gas with particular speed, they make it, then 1 kilohertz, 10 kilohertz speed, they make it to rotate. Then it looks like as if in liquids atoms are moving, here also spin systems are moving. Artificially they make it. Then I get wonderful, good high resolution spectral and individual peaks. Otherwise you don't get like individual peaks in a regular solid state NMR spectra. With that just correction, okay, this solid state NMR, though I have in this solid state NMR or NMR field for last 20 plus years, 25 years, I never recorded any spectra with respect to chemical shift or anything. It is completely solid state means in this type of solid state NMR. Though we operated that kind of a spectrometer, we never did that. Okay. Now, what we did here, we did multi-nuclear solid state NMR studies. They provide information about molecular structure as well as dynamics. As I told you in the morning, dynamics means what are all the motions which are happening on my face and hands and other things, all of them can be captured in one go, and along with that, any possible phase transitions present in the given system. Okay, that can be identified with this NMR relaxation data, and also whatever the conductivity mechanism happening in the system can be captured. Okay. And all these are important for any technological applications. Hence, all the details can be captured using this solid state NMR spectrometer. For our understanding purpose, I have taken two systems. One is trimethyl ammonium trichlorogermanate. It is basically, I have taken one ammonium chloride molecule, okay, that's similar analogous to that, and then I replaced every hydrogen atom with methyl group. Here at 3 places I have replaced hydrogen with methyl group and germanium metal I have taken and chlorine halide. One type of system we have taken, it is a perovskite system. Similar systems are used in our thermoelectric applications around. Very many other technological applications. Here we were able to identify the phase transitions, and also we were able to identify quantum rotational tunneling effects. As you know that quantum rotation, what is the difference between quantum rotation and tunneling? What is the meaning of tunneling? What is the general meaning? You know about it.
The particle can cross the potential.
Yes. If I cannot be able to jump over the barrier, this wall, I can always penetrate through the small hole. Okay. That phenomena, it is extremely hard to identify in certain systems. What happens whenever my temperature is high, I am able to jump over this wall. Okay, but whenever I cool down the temperature of the given system, I don't have thermal energy to make over. But still, you can identify me outside this medium. Then the possible mechanism is quantum rotational tunneling. Those can be identified with this particular technique. And the second, another representative example is tetramethyl ammonium hexafluorophosphate. Here we have different types of motions. One is I have a methyl group independent motion. I have methyl ammonium group independent motion. I have PF6 motion. Okay, all those motions can be captured with that, and whenever one hydrogen is coming back to the ground state, how well it gets connected to the fluorine atom in the molecule. How well relaxation mechanism of Lakshmi is connected to Shweta. Okay? Both of them are independent, but whenever they are sitting in the same system, they are always correlated. That kind of cross relaxation can also be identified with this kind of particular relaxation mechanism or relaxation type studies. Okay? Now let us consider trimethyl ammonium trichlorogermanate. What I do, as I mentioned in the morning, whenever atom gets excited or our nuclear system gets excited to a higher state, they come back to lower state. How much time they take to come back to their equilibrium state is called relaxation time, especially spin lattice relaxation time. That means that how much your neighboring people are able to grab you back to your equilibrium position. If spin lattice relaxation or your lattice is tightly bound, they pull you back immediately. Relaxation time is very less. Okay, immediately you will come back. If no one is there to bring you back, you take more time. That kind of spin lattice relaxation time we measure from approximately 400 Kelvin to, it is 10 Kelvin, 984, 98765, up to 5.2 Kelvin we made the measurement. Okay. This was done with our home built NMR spectrometer. We had the coolant system. We had the liquid. All of you know that, right? What is the boiling point of liquid nitrogen? 77 Kelvin. Okay. That is equivalent to 190 minus 195 degrees centigrade. What is the boiling point of liquid helium? 4.2 Kelvin exactly. Okay. Then whenever I told you in the morning, I take an inductor, I insert my sample tube, and then entire thing I insert it inside a cryostat. Okay, I make one cryostat like your water bottle. I make sure that liquid nitrogen is passing through the water bottle. From the top I insert it and then do the experiment. I have driven some wires to connect to the sample inductor and then record the NMR spectrometer. Entire thing is kept inside the external magnetic field. Okay, that's a very interesting experiment. Like that we have done. It is not so easy to do this low temperature experiment in your particular lab up to 4 Kelvin. Okay, we need to have our own setup, and also it requires lot of time. Okay, just to get one experimental data point, I would have spent about 3 weeks. Okay, like that to collect this entire temperature range, we have spent a year or so to collect the entire data set. Because lot more things, I have to create the vacuum, I have to go back to very ultra high vacuum, then only I will be able to achieve low temperature. Okay, that's why it is not like the way I showed the spectrum in the morning. In one shot, we don't get this complete data. Like this spin lattice relaxation, I measured it at 400 Kelvin, and then we noticed that the spin lattice relaxation kept on decreasing and reached one minimum point. At that point, relaxation time is minimum means coupling is maximum. There are many people to drag you back to the ground state immediately. Efficiency of transfer of your information or energy is more. And then again, when we notice that whenever as you are going down in temperature, from here your thermal energy is very less, then you don't have sufficient energy to bring you back. Then in principle you are supposed to take several days and years to come back to the ground state. But what happened when we kept on decreasing the temperature, immediately your relaxation time went down. Then also we were able to see that. Then we in the sense we were able to measure a small minimum associated with that. This kind of variation we fit to a particular data and we identified what is the energy required for that particular motion to happen. Okay, and always whenever you record your even at the MSc level or PhD level, when you show your experimental data, you always show error bars the way I have shown, wherever it is possible. Okay, the possibility what is this bar indicates, it is could be here, this could be here. This your experimental data point could be here or here. This is what I imagined it. Okay, when you show that authenticity, because in this picture it is not very much visible, that's why I have shown the blown up page. Okay. Whenever you report your data also, you always show that experimental error. How much is the experimental error? In the morning slide, whatever the osmotic pressure versus cross-sectional area, if you would have seen, one of the errors are this much. Okay, that's obviously people accept it. They know that how much difficulty associated in measuring that exact cross-sectional area accurately. That's why that is accepted. Okay, don't think that error bar makes you people believe, they don't believe you. They appreciate. Okay, but that more information is there in the fluctuation, not in the straight line. Okay, that information we could have neglected here. It is almost same. Is it not? Whenever you look at this complete spectrum, you always feel that it is almost same. Is it not? Whenever you look at that, you can see that how much, even if this point would have been here, even then this point would have been here. It's a clear minimum, one can see that. Okay, that's the indication of quantum rotational tunneling. And also when you look at this particular region, can you see that they are almost constantly coming down, right? I hope you are able to see that. But whenever same data, if I plot it in a different way, and if I plot it in this particular fashion, you can see that the way they are varying is different. Slope is not same, the way you assume that this entire thing is almost same. Okay? This clearly indicates that from here to here, system is behaving in one way, from this temperature to this temperature, it is behaving in different way, from this point onwards, it is behaving in different way. That means to say the system is undergoing phase transition, structural phase transition. That can be identified using this particular technique. And to cross-verify that particular phase transition happening in the system or not, we verify what is DSC. Have you heard of that? Differential scanning calorimetry. That is another study. What you do is you keep on sending heat energy to the system, okay? And when we change the temperature, you can see that small variations in the peaks. These peaks represent what phase transition is happening in the system. Exactly, if you look at the 272, you are able to see the change in the slope. Here 388 area, that is beyond the limit. Here between 317 and 325, the average value will be in between. At that point 323, I am able to see the slope change. Like the phase transition can be correlated with NMR and other well-established standard techniques. Yes.
What, like generally when you speak about keeping the keep it to be constant and varying the field and all. Whatever this slight variations you are observing, can't be, because in practicality you cannot keep magnetic field to be completely homogeneous. Right?
Yes.
So that could also be the reason.
For that we pay more attention whenever we make the measurement. The field homogeneity is the key point. That's why whenever this experiment was done using electromagnet. I make electromagnet, and then once I start sending large current through the electromagnet, that itself gets heated up. As you were starting in the morning, zone heating effect comes into picture. Fluctuation starts happening. Then to cool down the temperature effect, we used to send water next to that coil through which current was passing through to make it as magnet. Sometimes that was not sufficient. We used to keep on adding ice to the chilled water. We used to send it so that temperature, the fluctuation in the current passing through the coil is constant and magnetic field is constant. And this each data point was derived out of another 25 data points what we have taken. One of the what we talk as inverse square law. We talk about inversion recovery. Each data point is minimum number of points required to get one data point is 20 plus data points. What we used to do, it takes about 30 minutes to generate one of this data. Within the 30 minutes, any time small fluctuation can happen. That's why after taking 5 readings, again we go back to the first reading, whether if I change one of the parameter, I get back the first reading properly or not. Again I take another 5 readings. Again I go back to the first reading, whether anything got changed or not. Like that repeatability we have tested several times. That's why many people don't, they just send the sample. Why I told that this SSLMR is an independent technique for those reasons. Okay, that has been taken care. And like once this is for the first compound, another compound whenever we are having it, tetramethyl ammonium hexachlorophosphate. Again we are having tetramethyl ammonium means I have methyl group and also I have through 4 methyl groups connected to nitrogen group. Okay, it is something like that. This is my hand. Okay, this is one methyl group and one more methyl group at the top. Then there is one motion. Whatever the way I am moving, what is the speed at which I am moving, it can be measured. Other one is one methyl group itself is having one more C3 symmetry. How much speed at which they are rotating, they can measure it. This is tetramethyl ammonium group cation. There is another PF6 group also present over there. The PF6 themselves start rotating. But all of them are happening simultaneously. They are not waiting for ammonium group to stabilize before methyl group to start rotating. Vice versa. Hence, there is always correlation among these 3 different nuclei. That's why whenever I am seeing this proton NMR, we are seeing it over here. This phosphorus NMR was done by someone else before. In one of the references, they did it. Okay. Then I did for the same compound, I did it for the fluorine, I did it for the hydrogen. Again, as I told you, it is up to me to fix what should be the resonance frequency, depending on what is the magnetic field I am applying. To cross-check the repeatability of the experimental results, just for the proton itself, I measure it at 11 MHz, 16 MHz, 21 MHz. And whenever at high temperature region, all the data points should be same. Okay, the relaxation time doesn't depend on the frequency at which you operate in the high temperature range. I think one of the questions in the morning somebody was asking, how does it affect the temperature? Okay, at high temperature all of them are overlapping with each other. But at lower temperature we can see that this data point 21 MHz behaves differently, 16 MHz is having different relaxation time, 11.4 MHz is having different relaxation time. Okay, they are different in different temperature range. Okay, that would enable us, even if I intentionally did not add up the complex mathematical expression, associated with that. Okay, I can fit to all the data, I can get different peaks, all of them will be following same one. Here at this point is more important for me. At this point I am having minimum relaxation time, it is about 6 or 4 milliseconds. Okay, within 4 milliseconds they are grabbing him or taking them down. Okay, so that means your efficiency, relaxation time is minimum, relaxation strength is maximum. Okay, once I know that at what temperature I got the maximum relaxation strength, I can estimate what type of motion is happening, what is the coordination time associated with that. You will see he was talking in the morning, same is applicable here. Okay, that type of dynamics I can identify it. What is more interesting here is whenever this PF6, whether I do NMR of phosphorus or NMR of fluorine, both of them are associated with the same motion. Is it not? PF6 is rotating means whether I do phosphorus NMR or fluorine NMR, they are associated with the same motion. Hence, whenever I see minimum for the PF6, at the same point I see minimum associated with the fluorine NMR also. Like that, I am able to do multi-nuclear NMR for the same compound. Okay, these things, whenever I have to do, I have to change my operating system, I have to change the magnetic field. Okay, and I will get the data, and again this low temperature region again associated with the quantum rotational tunneling happening in the system. Okay, these kinds of fundamental details can be extracted by measuring the NMR data. Okay, I don't require very high sensitive NMR spectrum to do that. It is just like that, whenever the magnetization it shows one signal in your CRO, you start correcting that CRO magnitude of the intensity of the signal, just keep on monitoring as a function of temperature. I don't do Fourier transform, I never did Fourier transform for this afternoon data, only for the morning biomolecules I applied the Fourier transform. Here it was not required. Like that, I can always extract different ranges, I can identify different motions associated with that, and then just to show you that how this is the, just to scale you equation, okay, this kind of lengthy equations I have to write to fit this kind of a data. Okay, and then this demands you, I think, how many of you are using any software to fit your experimental data at MSc level? Are you analyzing any data? Okay, data analysis sometimes is useful. You can use that Origin software or any other MATLAB, any of the software. That is another soft skill you are going to learn. Okay, how to write y is equal to mx plus c. Just write, generate one data. Okay, write your own y is equal to mx plus c. It will show that what will be the slope of the curve. Okay, you can get started with that. And one of this, our university, I give this data, I make them to plot different temperature region, let them estimate the slope. The same thing can be done in normal graph sheet also, in a modified way. Okay, and then they calculate the slope and they give some fundamental constants. They estimate the activation energy required for the motion, different types of motion. Okay, how much energy is required for methyl group to rotate, go from one equilibrium position to another equilibrium position. You understood the equilibrium position? CH3 means all hydrogens are same and having 2 or 3 arms. Whenever I move, they look the same, but I move from one configuration to another configuration, C3 orientation. Whatever the rotation it is happening, that those details can be estimated. It is just for fun, and then they estimate, they identify, we provide this DSC data to them also. Then they correlate, yes, it is doable. It is not a major work. Okay, it's a simple work. Okay, from the data analysis also you do. And here, as I told you that these are all different motions associated with that. As you were talking about, this is corresponding to only fluorine, but the Lagrange frequency associated with the fluorine. It is Lagrange frequency associated with the motion to get the PF molecule. and here hydrogen and fluorine interaction, how it is happening, and here also hydrogen and fluorine interaction with respect to different types of motions. All of them clubbed together. Once I pick it, we can easily extract all these data. Here, even we estimated what would happen if there is no hydrogen contribution for river relaxation. Like Lakshmi and Vanasa, they are relaxing, another person is also able to dictate the relaxation. Okay, that's what, if that another person would not have been there, the data should have gone according to this dotted line. Because that fellow is influencing them, they are going to the other system. Okay, it is just to show that that's what we talked about, the cross relaxation. Your hydrogen is influencing body relaxation data. So those things can be estimated out of this kind of motions. Okay, that's all about the metal halide sound representative examples. Now we'll go with the.
If you are since fluorine is also having spin on a number to be half, so is your NMR whatever you are using, generally you will be mostly using either proton NMR or the carbon NMR.
That's where whenever you go to any commercial one NMR facility, we will only do those things. Since we had our own equipment, our own spectrometer, we were able to do this fluorine. And also the fun part of this one is, have you seen this Teflon tape?
Yeah.
What has happened? I still remember the day what has happened. One day my other friend in IISc campus, he did for the same compound, he did the proton NMR and probably one of the same compound. Here at that point he observed one of the relaxation data is around 60 milliseconds according to hydrogen. But what we used to do, whenever we take a coil, right? Coil is big, my sample after keeping it several times, it becomes expanded, right? It is expanded, then whenever I keep loose, again the same sample, it is so loose. For that we used to wrap it around with Teflon and then we used to make it tight and keep it easy. And then the next day the other person, I myself, I did the proton NMR, this fellow repeated the experiment because we were sharing the spectrometer. He repeated the experiment and when he measured the relaxation time, he got different number. I was literally in university, in UBC, I was teaching along with the way guest faculty man is teaching. I was also doing the same thing 20 years back. Then he called me, whatever the reading you took yesterday was completely bullshit. Okay, I am getting the correct value. See, my value is different, what you did yesterday was different. We were really surprised why I am getting. I was confident as it, Madam asked, right, I have done these many things, precautions, how can I go wrong? I argued. When I came back, when we did it again, then we noticed that the Teflon is having fluorine. We recorded the spectrum for the Teflon tail which was wound around the sun. That motivated us to do this entire fluorine NMR. Till then it was not in our list to do. And in our lab we never explored that fluorine NMR can be done the spectrometer.
From the proton NMR only you can do fluorine?
No. Same proton. Fluorine is also having spin-off nucleus, only the gamma value is slightly different.
Yeah.
Instead of doing it at one magnetic field, he did it on another magnetic field. Anyway, he got the signal, okay, nothing can give signal in this range. The difference is only 1 ampere difference of the current which has to be passed through. So the first diagnosis was, oh no, yesterday I kept it at 32.2 volts. Now you are doing it at 37.2 volts. How come you get the signal? Then when we did the literature survey, then we noticed that was coming from other nucleus, not this one. Literally from that day onwards, I explored this entire sample with that. Okay, that gave good result and wonderful physics associated with that. Okay, just to give you that how one can explore beyond that. Like that, then we talked about different concepts associated with that. Then we were able to see that. And the next one is what we are doing recently is that the internal field NMR. because now I have moved to another university, and later once I came back, I don't have that much energy to do 32 hours NMR from morning to next day morning. Literally, I used to start my experiments at 9 o'clock today till entire day till next day 4 o'clock. I used to do. Then my lab mate, she used to come back from master, and then she used to continue from morning 4 o'clock to next day 9 o'clock. I used to sleep in the same room. Okay, over there, and then I used to send her back to have food. Then I used to continue till next day evening. More than 36 hours we used to run one experiment, because the preparation itself is 2 days we used to do to collect it. Therefore, whatever the maximum number of data points we can collect it in one shot, we wanted to finish it up. That way, that sometimes research dedication is more important rather than intellectual quotient. Okay. And here, in the same way, this internal field NMR, whenever we have to do, we always go with the magnetic system. As you know that we have ferromagnetic system, antiferromagnetic system, perimagnetic system, and paramagnetic system. Okay, and whatever the samples we studied so far are diamagnetic systems. They do not have internal magnetic field by themselves. Okay, hence whenever we keep them inside the magnetic field, then only they get polarized in one direction and do on the rest of the studies. But here, all these systems are having this ferromagnetic system basically. Okay, they themselves align in one particular direction, and lot of magnetic field is generated at one point. It's okay, and then, as I already told that here both the conditions are same. Here externally I have to apply magnetic field to observe the resonance frequency omega, but here the internal field decides that what should be the resonance frequency, and then I can do these are the prominent nuclei I can do. The fun part or difficult part associated with this technique is your entire spectrometer. I'll come back to this kind of, this is the black diagram of the NMR spectrometer, what I have to do. Okay, here in this sample coil in the conventional method, I put magnetic field here and rest of the circuit remains same. But whenever I take my own system, this kind of ferromagnetic system, what I have to have is the resonance frequency for this iron is different, cobalt is different, nickel is different. Then my entire electronics I have to fine tune to match to the particular study. Earlier my job, though I did multi-nuclear, I was able to change the magnetic field. I can observe proton, phosphorus, fluoride easily. But here I don't have control over there. That system tells me what's the field you have to work to detect me. Hence, my entire electronics I have to rework on that to make it to work in that particular field. Just to give you what would be the internal field at the site of the nucleus of cobalt. These are the theory associated with that. Okay, for example, whenever we consider cobalt, it is I is equal to spin is 7/2 is the nuclear quantum number, the spin quantum number. Then the internal magnetic field is about 21 Tesla. It is a huge number. It is not easily achievable with regular methods. Okay, 21 Tesla is at the site of the cobalt what is present in the given count. Okay, that is not visible outside. When you have a cobalt system, you don't see that. It is only at the site of the nucleus. We have this much system. And then for a particular, there is associated magnetogallic ratio for that. Then my signal will be observed around 200 to 230 megahertz. I have to set up my electronics such a way that I can send the 230 megahertz from the signal generator and back on the signal. Okay. And then in a similar way for nickel, this is the typical system. For iron, the magnetic field is around 33 Tesla. Not outside. If I take 9, I don't get 33 Tesla. But if you are able to go to the site of the nucleus, the magnetic field generated is 33 Tesla because it has its own ferromagnetic ratio. The corresponding frequency will be about 45 to 47 megahertz. Okay, then my electronics I will fine tune that Then I record the NMR spectra. I run for these kinds of systems. Similarly, whenever I take alloys of iron cobalt, okay, then your frequency range changes. Whenever we take manganese systems, then the frequency goes up. Therefore, at my level, I need to have the entire electronic system which will be capable enough to work at that particular frequency. That is the realistic challenge. And also, I have to construct my LCR circuit, LCR resonance circuit, right? It has to match with 700 megahertz if I want to measure the signal. Okay, same LCR, basic concept, LCR, I have to choose it in such a way that resonance happens, minimum impedance associated with that, then only I get maximum current that will detect it properly. Okay. All those things are possible, and the basic spectrometer, if you look at that, basically these are all the different components associated with the new NMR spectrometer. NMR spectrometer. They look like junk. Okay. You can see that all these things, 1 meter, SWR meter, I have a coil, I have a catalyst, one of the amplifier, okay, one of the signal synthesizer, and then output. All these electronics you have to work out for this kind of a system. You need to, it's not like a commercial system. Just insert the sample and record the data. Go back. And here basically what we do, this is a signal generator. It generates some pulses. First I mix, only signal is applied to the coil only during small time period. Okay, it is about 1 microsecond or 1.2 microsecond in the pulse width. Only during 1 microsecond you apply, like I shine the light sharp gold, right? Then I measure it, what is the relaxation. How does my material behave? Like that we measure it, and then since it is insensitive technique, it requires high power. I use high power amplifier, 1 kilowatt amplifier I use it. I make, this is about 2 volts peak to peak, goes up to 200 volts peak to peak. Right. Okay. Like
it can used to power liquid nitrogen or helium also.
Yeah, here we do that. Here the sample coil, especially for iron NMR, I cannot do room temperature. The signal strength is too poor. Only cobalt I can do that. That's why whatever the spectrometer we are setting up in our university now, all this work I did it at IAC. Okay, in of science, now the professor and my grandfather, academic grandfather, everybody retired. Then I shifted that equipment to Ramaiah University. Now we are almost in the final stage of setting up to do that experiment. Replicating this itself is like a PhD problem. I know what are the problems associated with that. Every component we have to rebuild. Therefore, this entire sample is inserted in the liquid nitrogen. As you know that, all of you have learned about population inversion, or you know that the Boltzmann distribution, right? N2 is equal to N0, or N1 is equal to N0 into the power of delta V by kT. If temperature is low, the population difference is more. When population difference is more atoms can go up and come back. Okay, that means if I want to increase the intensity of the signal, I have to decrease the temperature. At room temperature, the difference is so small. Just to tell you that whenever I showed the 2 energy levels, if 2,000 people are sitting in this floor, ground floor or the ground state, only 2,001 number of people are sitting in the excited state. Only one person is causing the NMR signal to be detected. Extremely insensitive technique. That's why many people don't work with that. For that purpose, we went for this low temperature. Whenever I do that, I can increase the difference as 10 times, minimum 5 times I can increase. Like that, there are many other challenges associated with that. Why it becomes important, and also people recognize work associated with that. Like this, all these are all once signal comes here, there is a transcoupler. What happens whenever high power goes connected to the coil, it connects from here to here, and then here very microvolts will be generated as EMF whenever atoms come back to the lower state. Then that microvolts come, then this is coupled to the receiver section, it decouples from the transmitter section. That's why we call it as PR switch. Okay, it is like a switch where more people are coming, alone, then when few numbers are going through the back door. Like this is the transmitter, there is the receiver. That kind of dedicated double balance mixers we use it. And we said at that point that this one can be detected through normal digital oscilloscope and can be recorded through PC also. Okay, these are the associated come to the overview of the NMR spectrometer as far as internal field NMR is concerned. Today morning we were talking to Professor Krishnaveni, and she was speaking about how much? 5 crores for NMR spectrometer. Okay. This NMR is for 25 to 30 lakhs. You can imagine the difference between those two. Of course, there are many other advantages, as I told you, that only the ferromagnetic systems can be studied here. And you need to have expertise in this field to do that work. But any operator with 15 days training, any person can operate it. But these kinds of work cannot be done. Okay? And if you would have carefully looked at my earlier slide, if the operation frequency is low, I have no information. All high resolution spectrometers, they work at 900 megahertz, 800 megahertz. That is of no use for this kind of dynamics measurement. If I want to do dynamics measurements, I have to go down. If I am able to do same experiment at 1 megahertz, I will be the happiest person. 1 megahertz means relaxation, slow motions. If you take 1 year to rotate this much, with that technique I will be able to do that. Okay, that's how it goes through that. Any slow motions, if I want to measure it, I have to do it at low frequency. And here, whenever we did the same content here, our skill set is the key for this kind of NMR to be done. Okay. And once you know that same nickel ferrite, talked about the iron, right? We'll be having nickel ferrite in the spinel ferrites, magnetic systems. Okay. And your iron can occupy at 2 different locations. Okay, at nickel locations also it can go whenever I keep on changing the concentration of this iron. The way they started as doping aluminum in place of iron. Okay, iron can go to 2 different locations the way it is shown here. Okay, either it will be the tetrahedral site or octahedral site it will go. And then I am getting 2 signals. Whenever the iron is going and occupying octahedral site, my resonance frequency will be different. Whenever it gets into the tetrahedral site, it shows NMR signal at another frequency. By measuring this signal intensity at different frequencies, I can say that where my cation is going and occupying. How ion distribution can be studied using that. This was done with our PhD students. Okay, and same thing we can do. This is, I've heard of this. Are you able to recognize that? What is this graph? BH curve, VSM, variable sample magnetometry. Okay, with that it can measure that what is the maximum magnetic saturation magnetization associated with that. Then this is where you just do the sample, they will do the data collection and they will give you. But this fellow only measures what is the total magnetization of the sample. It cannot distinguish how much is in the B side, how much is in this hexagonal state, sorry, tetrahedral site and octahedral site. What is the distribution of atoms, it cannot measure. You can only say your magnetic field is high, magnetization is high here for this composition or low for this composition. Micro level estimation is not possible using conventional techniques. Okay, hence we go with this method, and as I told that it has 2 sides. Okay, and whenever I perform same sample with NMR, as you can see that NCFO0 means it is your this is another system. Instead of iron, I kept on adding cadmium system. Okay. And whenever I change the cadmium concentration, when I increase 0.1% of cadmium at the iron side, and when I did iron NMR, 57 Fe IFNMR studies, you could see initially I had 2 peaks. Then when I kept on increasing the cadmium concentration in the diatomic diamagnetic system, okay, then they started merging together and finally it became only 1 peak. We did this systematic measurement. Then we know that within that 1 peak also there are different contributions. How your domains are created within the system, how domain walls are created, and how amplification is happening at the domain wall position. All those things can be estimated by measuring these. By deconvoluting and fitting to the different contributions, they can estimate. That would really help us to measure the cation distribution, exactly how much of the aluminum or iron is going and sitting in octahedral side or tetrahedral side. Like this cation distribution can be measured using this technique efficiently. And for example, another one is cobalt. We took one cobalt system, and we usually whenever we have pure cobalt system, it follows this kind of a morphology. When you start adding nickel to the system, what happens again? That takes different shapes. As you can see, the cell images of cobalt 90 and 10, it is following like structure. Okay, that structure modifies as soon as I am increasing the nickel composition. But whenever I go to nickel is 40% and onwards, okay, we don't have much of the data here because the moment nickel concentration is more, my NMR signal vanishes. I cannot record the NMR of that sample. That's why we did not record the cell image associated with that. Okay, how the morphology of the given system can be changed by the composition. Okay, and I can measure. This work is done by a PhD student. Just submission thesis. Okay, he worked on that. He can be able to identify how many neighboring atoms are contributing to each signal. Okay, how many cobalt atoms I am having, how many nearby or nickel atoms are contributing to that. As you can see that how all the peaks are towards higher frequencies. As we keep on increasing the concentration, all of them are getting distributed equally. You can see that almost all of them are distributed equally. Therefore, the nickel is going and occupying at all the cobalt nearby systems. Okay, and they give different contribution or different conclusion you can draw out of this kind of behavior. This is when I do VSL, it only shows that the magnetization is going up or coming down. It doesn't give microscopic information from that. Okay. Oh. Now, same thing, if I have to represent it in a quantitative way, I can estimate what is the composition of each atom, or the values are correlated. But the basic composition over there is crystallographic phases, whether it is FCC and BCC. One of the data I did not show you. Okay, one of this other IFNMR data, if I have to show you, here you can see that different peaks are observing at different frequencies whenever I take only pure cobalt system. Whenever I prepare the cobalt system with one of the solvent as only water, and sometimes I use ethanol, then I get different phases. Though you follow rest of the methods, say what solvent you use to synthesize the cobalt, it is extremely hard to get pure HCP hexagonal close packing phase of the cobalt system. What we try to do in this case, we use different solvent systems and we measure the NMR. And when we did that work, as you can see that whenever we are using the full system, okay, it follows the FCC, and whenever we use complete system with ethanol as a solvent, it shows different morphology. Here it shows different morphology. Okay, but whenever I do XRD here and whenever I use water, it follows different morphology. Okay, and this is a commercial compound. This is with water. This is with ethanol. You can see the different morphology associated with that. But the problem here is that Mani said in the morning hours, your FCC and HCP, whenever we do XRD, there are 3 peaks common for both the phases. Okay. For example, 3 peaks here, whatever the peak we see here, 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 all the peaks are same for both FCC as well as HCP. It is hard to distinguish my prepared compound is following HCP phase or FCC phase. Similarly, you can see here 200 for the FCC phase and 110 for HCP phase. Both of them will give the peak. Here I am observing in both the places. How can I identify, quantify exactly what is the composition of HCP phase? How much percentage of FCC phase has been formed using different samples? Okay, that is halfway Rama, halfway Krishna. Okay, because both Rama and Krishna are having 3 characteristic properties. Both of them become angry, both of them are friendly. Okay, only one parameter is different. If I want to quantify how much of Rama and how much of Krishna, it is hard. Same way here, it is hard to identify which phase has formed correctly. Hence, we go with IFNMR technique. Because I know that whenever it is following HCP phase, it shows different NMR spectra. Whenever it shows FCC phase, it has different sign. Hence, we did different methods. Whenever we have ethanol, it is at higher frequencies. Okay. Whenever commercial compound shows this kind of a peak, but whenever we are having equal percentage, you can see that one is towards the left, one is towards the right. Here it spreads over from this side to this side. This is the overlapping of both the phases. The beauty of that is I can quantitatively with this kind of simulation, okay, deconvolution of the entire spectra, I can quantitatively identify what is the percentage of FCC phase, what is the percentage of HCP phase. Okay, that kind of quantitative measurements, cation distribution can be done using this technique. Like these are the representative examples with different system. Okay, and the same information sometimes it got repeated when I was trying to do this. These are all like same thing can be extended for films and other things. We are trying to explore some more systems. Okay, can be studied using this kind of IFNMR studies. One is regular work we can do. If you do not have facilities to have that, we can build our own spectrometer and we can study over here. Same cadmium system as I told you, different whether when does it become normal spinel system to inverse spinel system also can be estimated when measuring the lattice parameter with XRD. That can be correlated with the NMR. Okay, and these are the finer details of the exact composition can be measured, and these are the additional work. Okay, whatever the details, I think the conclusions are from morning session. From NMR, I can distinguish undulations at what point they dominate, at what point I will be having protrusion forces. Okay, as I was talking in the morning session, the connecting details can be distinguished efficiently, and from proton NMR and fluorine NMR, I can identify quantum rotation tunneling, and phase transitions can be quantitatively measured, and zero field NMR, as you have seen, that it's a wonderful tool for ferromagnetic systems. Only limitation is they should be magnetic systems. Okay, other two techniques we can use at different places. Okay, and these are all finer details associated with that, the biophysics, whatever the morning session I was talking about, how different curvature effect comes into picture, how tension calculations can be done, okay, how undulations can be done, and this is 2012 Nobel Prize, we got it for identifying this crystal structure through NMR. Just to, he extended up to this kind of a complex system, how they are able to predict what is the distance between these two, they can be able to predict using NMR. That's what we call as tertiary structure, secondary structure. Okay, what we know is our normal composition, NH3O4, some other composition, and then we go to molecular formula and chemical formula to molecular structure. After that, this is the real structure of any protein. Okay, if I have to exactly predict where is the beta sheet, okay, we can always do it with high resolution NMR. These things I cannot do it with my home built rack NMR. I have to go with, I have to spend 10 crores, 15 crores minimum, and to maintain the liquid nitrogen and helium, I have to keep another 1 crore in my pocket for every year. Okay, lot more. Those things cannot be done with normal spectrometer, what I mentioned in the latest stage. Okay, and this is the same continuation of that, lot more work. This is my US group, and unfortunately I don't have my present the PhD students group photo. I forgot to collect it from them. Okay, and at this point, whatever the later part today in the second half I talked about, it is published in this textbook. Okay, this is prescribed in some of the universities also, and all those, and recently we published in our spinel ferrite systems, one of the book chapters, where it talks about these magnetic systems where one can study for gas sensing applications, for photocatalytic application. Okay, what are the importance of ferrite systems, purely based on ferrite systems. Let's just appear last month or this month, last day of the month. Okay, all this is all, these are all other data points. With that, I don't have dedicated thank you slide. Okay, it is just, sorry, I used to give talk, as you know that we always copy and paste some of the slides. Okay. This is earlier, we had this KQI to join our IAC. Okay, but unfortunately we stopped now. Okay, you can join IAC if you are, anyway, all of you have already joined for your MSc. Okay, for this, I heard that. I am happy to inform you, or I was happy to hear that most of you are able to clear the gate and other competitive exams. Please keep it up. Okay, keep up your tempo and try to answer all the questions, whatever the previous question papers solve, and make your own study group. I think all of you are already doing that. Those who are lagging behind, please do so. Okay, and you can join IASC. Once you clear these exams, you can become a PhD student. If you have cleared this JAM exam, you could have become an integrated PhD student of IASC. Before joining Ramaiah, I was taking care of integrated PhD program at IASC physics. Okay, and since you have already missed that bus, you have these 3 buses. Okay, you can clear this exam and join as a PhD student, and if you do PhD, if you are doing it, explore one of the options for postdoc. None of the are get collaborated with them because some part of the work, and then if you are able to do good PhD and good postdoc at some other place, you can come and join IASC as faculty. And if you join faculty at some other university, do extraordinary work, outstanding work, come and join the university IASC as a director itself. I'm not telling the joke, it happened. All of you might be knowing that the Central University of Hyderabad guy became the director. Okay, I'm not exaggerating. All the options, don't think that I have already settled down here or this is my limit. There is no limit. As I already told in the morning, if I can do this way, all of you can do. Okay, you don't require extraordinary efforts. Okay, but your consistency is extremely important. Okay, that's it. And I am thankful to Professor Krishnaveni madam and the entire team, and that all of you are taking individual responsibility and contributing it to your own aid. And thank you, Madhu also has come, my friend. Okay, happy to see most of the known faces. Thank you for your patience.
Now the session is open for the queries. Do you have any questions?
Sir, in your previous slides, sir, regarding the ferrites, you mentioned the distribution of divalent and trivalent metal ions in
Yes, sir.
tetravalent and octavalent
Yes.
sites. Is there any formula, sir?
No, it's not the formula, sir. Whatever
One more
we-
slide, sir.
Here.
This one, sir.
Here,
And the previous ones.
yeah, same information. What we do over there here is how many nickel atoms are there, how many iron atoms are there at B site and A site. Okay, what happens? B site only contains nickel atoms. Okay, and your both at B site and A site iron gets distributed. It can go to B site or A site. It has ability, but again your cadmium cannot go to B site. Okay, iron has ability to play a dual role. Hence, whatever is here plus this one should come out to be same. That can distribute 50% here, 60% over there, 20% here, 70% over there. Like that. Based on that, that is estimated out of the whatever the intensity of the signal here.
But there you mentioned from hexadecimal.
No, this
Previous
is
slide.
that
That is
people
from-
do with Professor Madhu, who is sitting the back, is expert in this
Because you mentioned
Ritfield
from
analysis. This
Ritfield
why
enhancement.
we have shown here is from Ritfield analysis also it is extracted, and from nominal composition what we were expecting, from Ritfield analysis, from IFNMR also we are able to distinguish that. Again, if I have to do this kind of distinction, they have to identify, for example, there are 5 peaks for HCP and 5 peaks for FCC. Among them, 3 are common. I cannot take them to
But there in the nickel cobalt ferrite, it is in simple cubic.
simple cubic. That's why
It is not
three,
in.
3 peaks are common for both, whether it is in FCC or HCP.
But simple cubic is different, sir.
No, what I mean to say, I am trying to give overview over here. Okay? Yes.
So when it comes to XRD, we mostly take into account Wyckoff positions. Wyckoff positions are the atomic positions. So for A side, there is a specific Wyckoff position, and for B side, there is a specific Wyckoff position. And when we do this mixing, it is with respect to playing with Wyckoff positions and the occupancy of the A side and B side. So
A side
even though it
will-
may be simple cubic, but for A side and B side, there will be separate Wyckoff positions.
Divalent metal ions will go to A site and the
Yes,
trivalent will
because
go to
see,
B site.
the simplest spinel is the Fe3O4. So Fe3O4, it is having one Fe in 2 plus, 2 Fe in 3 plus. So that is how you get Fe3O4. And even in this case, so your Fe can go to nickel side. That is possible because nickel in 2 plus. So, but not the cadmium. Cadmium, it's always not having any.
Yeah, it is always in the A side. I think what I misleaded or I was trying to say that the similar composition what I did it for the cobalt, I was trying to give the answer. I think he answered that. Okay, I just looked at the overview and I was trying to explain. Okay, yeah, this is there is no HCP, there is no cobalt system associated with that. Yes, it's a observation. Okay, but in some of our recent.
But there is a formula, sir. Manually also you can do that.
No, that's what the
Distribution of
nominal
divalent and-
composition we have taken. Nominal composition means manually we have done that. And then with XRD, with Ritfield, in the latest papers we did it with Raman studies also. I have not touched upon the two usable and Raman studies, whatever the work we did it. And our recent paper, what we have submitted on the FTIR also, we try to connect it to the same system, nickel cadmium system. Okay, I have not talked about that because that is not yet published. Over here. This is in one of, and the same studies can be done with mass bar. With mass bar also we get all this, the way I got different peaks, right? In one of the paper where I am not directly part of that, we have compared it from mass bar, from VSM, from NMR, from XRD. All of them are matching very well along with Raman studies. All those things are there in some of our publications. We just chose representative samples and like this. Give the overview of that instead of getting into quantitative. Thank you.